Hello everyone, and welcome to our class in Artificial Intelligence and Machine Learning in Finance. Now, in this video, we want to continue our application of k-nearest neighbors and support vector machines in the context of predicting class labels related to customer churn, related to the termination of credit card contracts. So we've already seen the data pre-processing, we've seen the data, and we want to start with k-nearest neighbor. So for k-nearest neighbor, we here rely on the Euclidean distance. We could have also used the Manhattan distance, the cosine distance, any other metric that measures the distance between two observations. And as we remember, k-nearest neighbor is called k-nearest neighbor because we still need to decide on if we want to use 5 neighbors, 10 neighbors, 20 neighbors, etc. So the number of neighbors is a hyperparameter. It's a parameter that we need to set in order to train our model, and we determine the appropriate, in a way, optimal value via tenfold cross-validation. You can also do these computations in parallel, and as you will see later on in R, actually we are using a cluster and we use parallel computing to speed up the estimation process. This is not really necessary in this context, but I wanted to include this here to show you how you can use parallel computing to get to results quicker. We determine the optimal parameter and evaluate a model's predictive performance, that is how well we are able to predict the positive class label, based on the two metrics accuracy and Cohen's kappa, and we'll have some more details on these two metrics later on. Now we start again by loading the library caret, and we set the TR control object, which is simply a container for some options how to train our model. By using this function train control, we set the method to cross-validation CV. We want to do tenfold cross-validation, so number is equal to 10. And then in line 3 again, in order to be able to reproduce and to replicate our results, we use the setseed command. Then the cross-validation is done in parallel. If you do encounter any problems with the PSOC cluster, then you should simply comment this out and do the cross-validation on your computer solely. So the library you need is do parallel, and CL is make PSOC cluster 6, so we are using 6 cores or threads, and then we register do parallel with this object CL. Into KNN model, this object, we are writing the results of our trained model. We train based on the xtrain scaled data object. We use as our response ytrain. We use KNN, k-nearest neighbor, as the method. We will set the tune grid to a grid that expands from 1 to 10. What does it mean? Well, tune grid specifies the tuning parameters to train over the model. So we're considering 1, 2, 3, and so on, 10 neighbors in the end. And then we are using the result of our cross-validation TR control, and the metric that is used to look at the accuracy of our model is actually the accuracy, and then we stop the cluster. Okay. We print the result after having done our training. So the optimal number of neighbors is actually the same here for both accuracy and Cohen's kappa. In general, this is not necessarily the case. In this scenario here it is, and as we can see, we see the resampling results across tuning parameters for accuracy, kappa, and 1, 2, 3 up to 10 neighbors, and accuracy was used to select the optimal model, and the final model was 6. So we are ending up with a 6 nearest neighbor model that we train on our data. To see the predictive performance, we predict the class labels for the test data set. This is done using predict. Where's my cursor? It is, okay. So we use predict, we use the fitted and trained k-nearest KNN model object, and the new data is x test scaled rather than X trained scaled. We will see that these are the predictions, and then we can use the so-called confusion matrix, also error matrix, to compare our predicted response variables with the reference data, which is y-test. So we are actually doing an out-of-sample forecasting accuracy or prediction accuracy test, and this is done in the so-called confusion matrix or error matrix, which is quite common in machine learning. This is the confusion matrix. What you can see here is, let me highlight this. Here is my cursor again. Here it is. The red dot is a little bit small. So you can see here in this first part, this is a simple matrix that compares the predicted class labels, in this case attributed customers and existing customers, in comparison with the observations in the reference data set. So we have attributed customers and existing customers, and as you can see, this is fine and this is fine. It means that actually those that actually were attributed customers were also predicted as attributed customers, and the existing ones, 1,672, were also existing. And, well, not surprisingly, if we use red line here, this one is not good, and this one is also bad for our prediction accuracy. Why? Because these are observations that fall into class 1 and are attributed to class 2 and vice versa. So these are the errors our prediction has done. So we also can see the accuracy, a confidence interval for accuracy, the no information rate, and Cohen's kappa, and some other metrics, and we want to comment on these now. So accuracy is actually defined very simply as the percentage of correctly classified observations, and in our example, well, not surprisingly, we have 189 plus 1,672 divided by the total number of observations, which is 189, 1,672, and those one that were erroneously attributed to one of the two classes, and thus we get an accuracy of 90%. The no information rate is defined as the largest proportion of the observed classes. In our example, this corresponds to the proportion of existing customers. So we take 53 plus 1,672, again divided by the total number of observations. So it's the highest accuracy which can be achieved by constant prediction, meaning what? If, for example, we say attributed is 1, termination is 1, existing customer is 0, and let's say this is our data set. This is our data set. Then we could simply say, well, let's do it constantly. So let's say a little bit some more. Okay, let's say 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. How much and how many observations would we get right? 1, 2, 3, 4, 5 out of 2, 4, 6, 9. Same could be done, let's say, if we say it's 0. The red X is a 0. So 1, 2, 3, 4, and so on. So we are simply saying we don't do any prediction at all. We simply set it all constant to 1 or 0. And the no information rate then is the highest accuracy which you can achieve by a constant prediction. In this case, this would be a constant 1. If we simply say everyone is attributed, I think this is the first. Let's we just check. No, it's actually the existing customers, so no termination. And this is the highest accuracy which we can achieve simply by setting all predictions to 1 or to 0. You have to decide which one is better, of course. Then Cohen's kappa is a measure of a classifier's performance relative to how well the model would have fared simply by chance. Therefore, you compare the accuracy of the model to the hypothetical probability of an agreement by chance. And in our example, the no information rate was 84%, 83%. They belong to existing customers, while 16.51% belong to the attrited customers. And the K nearest neighbor model classifies 88% as existing and 11.7% as attrited customers. So the probability for an agreement by chance can be calculated as you take the 83% times the 88% and the 16% for the attrited customers times the 11.71%, and this gives us 75.65%. And Cohen's kappa is now defined as the accuracy minus this probability divided by 1 minus this probability, and it gives you 0.5926. That's Cohen's kappa. When you compare two models, a higher kappa signals a better predictive performance, and the maximum value is 1. However, there is no standardized way of interpreting its values. So if you have two models, take the one with a higher Cohen's kappa. A negative value of kappa would signal that the model's predictions are worse than predicting by chance. So this is even worse than, I guess, setting it all constantly to 1. Now, we have some additional metrics, error costs of positives. In our example, this is the customers who terminate their contracts, and negatives. They are usually different. And in this context, sensitivity and specificity are more informative than accuracy. So we start with sensitivity. That's the recall or true positive rate is defined as the number of correct positive predictions divided by the total number of positives. That's 55%. And specificity is true negative rate, and that's the number of correct negative predictions divided by the total number of negatives, and it's 96.93%. In our case, the K nearest neighbor classifier is good in predicting customers that do not terminate their credit card contract, but bad in predicting customers that do. And what is the possible reason? What's the problem here? Well, if you remember, we have a highly unbalanced data sample. Only few terminations, a lot of customers who stay with us, so it's quite difficult, based on this data sample, to achieve a higher sensitivity. That's the reason. Okay, so this is the example of the K nearest neighbor classifier, and in the next video, we'll look at the support vector machines.